Yeah, thank you so much for having me here. It's been a pleasure the whole week listening to everyone's talks. So this is my outline of the talk. I will first go over deriving sterile neutrino constraints from gravitational strong lens quad systems. And then I will discuss a bit about what the future will bring for us in this particular area. And then I will go over a couple of ongoing works and hopeful steps that we can take towards preparing for that future. So, similar to the talk you just heard of, we use gravitational strong lensing as applied to quasars, and they are lensed by lens galaxy, and we see the images that are formed basically by the impact of the distribution of the substructure in the halos of the main lens systems. These are examples of how the actual observations look like from Anna Nirenberg's papers. And maybe intuitively, when you look at them, you may not be like, oh my God, this is going to be, you know, the precision measurement of dark matter. But but turns out it's actually really cool, a really cool probe to be able to infer that. I'm so sorry. Yeah. So the key here is the fact that all galaxies form at actual nodes of dark matter filaments. And it's also very convenient for us that different particles of dark matter result in different substructure formation at the level of halos and subhalos that can be probed with this technique. So if we have our favorite model of dark matter, all one has to do, though it may not be so direct, is calculate the phase distribution function, pass it into class, get the transfer function from there, and then use the initial conditions that are basically given by the CMB measurements. You know, you can't really tweak that much. And then propagate that structure formation further to the power spectrum and calculate in a linear regime the halo mass function, and then in the nonlinear regime the subhalo mass function. So this all sounds good, except when we think about the fact that one will have to generate this for every mass proposal for the given particle. So if we want to compare to data, any sort of posterior on a mass distribution will have to technically know how the structure formation would look like through entire n-body simulations for each proposal of that mass. So this is why n-body simulations are so important in our field, and thank you so much for working on it. And the trick that we use is basically take the results from the n-body simulations and interpolate the behaviors of what would be the formation, basically the formation structure for particle masses that are sampled in between the ones that the simulations were run for. So for this analysis, we actually use Galacticus, which is a semi-analytical code developed by Andrew Benson and his research group. And the advantage of it is that being semi-analytical, it doesn't actually take us much time as n-body simulations, but it is using the recipes derived in n-body simulations. And it's basically creating merger trees, and based on these merger trees, we can construct halo and subhalo mass functions for a given dark matter model. So basically, this step is, these 3 steps are covered by the Galacticus thing. So in this particular research project, I was looking at the KEV regimes of dark matter models. So these are known as also warm dark matter. That's also one of the models that is in that regime. It's also very well sampled by the gravitational lens approach. So one of such dark matter model is the sterile neutrino. The stellar neutrinos take their name from the fact that neutrinos being fermions, they have spins, and basically the weak force interacts only with left-handed neutrinos, which are basically one type of spin. So we believe that if there's the other type of spin available as well, it may not interact with the weak force. So those are called sterile by night interaction. Of course, other particles that don't interact with any force, even dark matter, you could call it sterile from the point of view of not interacting with set force, like E and M. But in this case, it just refers to not interacting with the weak force. And I looked at 4 different stellar neutrino models that have different production mechanisms. And what we do is, this is an image from Daniel Gilman's 2020 analysis that he just talked about earlier, is we try to match the photometry of the images as well as the positions for them. And the proposals sample from the halo mass functions of the theoretical model that's being studied. And statistically, we just look over multiple realizations of for each quad system in the set. So this is a plot of the posterior that Daniel inferred in his paper for the half-mode mass, basically. And here you can see something very clearly, like there's no going to 0 on the left side. So basically, this creates there may be dragons, as they say, over there. So we can only put a limit from this analysis, not a constraint right now. So what people have done through basically the same embodied simulations that I described before is they have inferred relationships between what would be the thermal relic warm dark matter and the half-mode mass for a given Hill mass function. So I was using the recipes from Schneider et al. From 2012, and the 2 curves here come from basically making 2 different assumptions about the conversion between the exact half-mode mass in length and the conversion to the actual mass itself, that require a different assumption about the density of the universe, whether or not it includes the baryons as well. So for stellar neutrinos I was looking at, I think this was mentioned earlier in the conference as well, there's a similarity in the transfer functions themselves that allows a very simple mapping between the different energy levels in a given stellar neutrino models and the thermal relic warm dark matter. So this basically simplifies the analysis a lot because one does not have to run the whole pipeline again. So what I did is I inferred a conversion relationship between the mass functions of the stellar neutrinos and the thermal relic warm dark matter, and then I transferred the posteriors that were measured for each stellar neutrino model, obtaining a 95% lower limit on all of them. And this is also based on Simona Vegetti's work in 2018, where she was constraining the Schiff-Fuller model. So I basically, our limits are basically below the red line of 7. So it's a pretty strong constraint over there. But these are all so far constraints from strong gravitational lensing. And because this mapping was simply a mapping into the thermal relic warm dark matter, there are other works that have constrained thermal relic warm dark matter from other techniques in physics, like the galaxy satellite counts from Ethan's work, and Lyman-Alsop forest as well. So I wanted to see if we can sort of combine this and what are the limits when one combines these together. And these were the results. So obviously the limits are stronger when all of these techniques are combined together. There is actually no possibility right now to combine exactly all 4 together. So like the papers are either combining strong lensing with galaxy counts or Lyman-Alsop for a separate. So it would be really cool to do an analysis across all 3 at the same time. The GitHub repository is available publicly. You can basically reproduce everything that was done in this analysis using it. So the other part I want to talk to you about is what about the future? So this work I just showed actually used only 8 quad systems to get at the time what were the most stringent constraints on forced radiometry models. So the nice thing is that we have Euclid already basically coming out and giving us data, and LSST. And there's forecasting that predicts that there will be 8,000 lens quasars discovered, out of which 3,000 can be used for measured time delay, related to a question that was before in the audience as well. And about 1,200 would be quad systems. So we will hopefully move from 8 to thousands, basically, in the span of the next 5 to 10 years. So the path here is to basically conform the lens systems by determining the redshift and identifying that there's a foreground and a background galaxy involved in the system, and then by measuring the spectrum of the actual lensed images. And then propose follow-up with the very precise, basically measurements, like either JWST, HST, or from the ground. So in the analysis of lens images from Anna Nirenberg's work, basically, in addition to just looking at the quads themselves, one takes advantage of the fact that we can measure the spectra of the images themselves and separate basically the contributions between the narrow line emission and broadband emission. So this plays so a big role in this play adaptive optic systems that can actually correct basically the point spread function for the contribution of the atmosphere for the case of the telescopes on the ground. So I will be talking about upcoming improvements that have to do with both AO upgrades, but also detector upgrades on this side. So right now at the Keck telescope, we have the series detector and the current AO system, but we are going to see soon the Kappa adaptive optic system installed, which is being basically commissioned at the end of 2024, and is probably going to be giving data in 2025. And then the detector is going to be upgraded to the Liger system. This is an improvement in the number of pixels on the spectrograph side by a factor of 2, and in the resolution of it as well. And this is the same detector instrument that's actually going to be used for the TMT. It has a different name. It's called IRIS for the TMT, but it's the same team developing it, and it's identical. And then finally, I looked at the adaptive optic systems for Enfirawos, which will also go on the TMT. So the very nice improvements here are coming also from the readout noise and the dark current that are going low, basically as the detectors are getting better, including the changes in the pixel size. So one big expectation from the adaptive optic system is that it's going to change the way that the correction for the atmosphere is going to be done. So there is a prediction that basically kappa will bring the sterile ratio from basically 0.2 to 0.8 in ideal conditions. So that's pretty exciting. So I simulated basically the observed point spread functions I took the observed point spread function from the current measurements from Keck, and then used the simulated PSFs for kappa and for Enfirawos. So these are given an assumption of strail of somewhere between, it's variable. I could tune it in analysis, but these ones are done for like 0.5. And then I took for 3 different quad lens systems that are also observed nowadays, and I simulated their appearance as they would look like to the system with the given PSFs. So on the left here we have basically the effect of the point spread function and then the addition of the noise. And this is what the images are flashing are the subsequent improvements as the instruments are getting commissioned. Basically, first the new adaptive optics systems, then the detector at Keck, and then finally the TMT. So after I simulated the images, what I did is I tried to actually model the photometry and astrometry that will come out of these systems. So in that model, one wants to reconstruct the PSFs and the noise, and then also infer the astrometric positions, and we included the galaxy profile as well, and reconstructed the photometry. So these are the posteriors and the photometry from the resulting measurements, and this is a comparison between the different stages of the experiments. And what's very helpful here is that we can actually tie these flux ratios to what we hope would be inference on the halo mass functions themselves. So I really liked Ting's question earlier this week when she said, it would be really good if we could perform forecasting for our analysis. So that's basically what we try to do with this work. So this is a paper from Daniel as well from 2019 when he was calculating the improvements on the half mode mass based on the flux uncertainties and the number of lenses. So in this work, what we saw was that the flux ratio uncertainties are actually going to be below 2%. So we're actually going to go under this prediction, which was stopping here at 2% and at 10 to the power of 7 solar masses. So it's worth it right now to basically try to simulate this to even lower halos to see where we are. So these were the precision in milliarc seconds for the astrometry. So we see that we basically go to sub-milliarc second precision on the location. And for the flux ratios, depending on the system, we go from under 2% to under 0.5%, depending on whether or not we assume that point span function is known. So these new systems are going to have PSF inference built into the system. So we'll see how well that works. And whether or not there's a galaxy present in terms of the light profile, because some quads have galaxies, some do not. So overall, this is sort of very good time to do this sort of work because Euclid and Rubin are basically going to ensure a movement of numbers to hundreds, if not thousands, and then we'll be able to do very precise measurements. And the important aspect of this very short, small precisions is that we can basically decrease the exposure time. Like right now, we expose an object to about 10 minutes. But with the new systems, we will be able to get them in about 1 minute. So it makes follow-up of 1,000 systems actually realistic. And also just wanted to mention that SNOMAS identified astrophysical probes of dark matter as high-priority research, so it's good. So what does the future bring? Pretty much awesomeness, amazingness. And then just wanted to give a shout-out that I think forecasting results actually help motivate funding. So please do follow what Ting was saying to try to basically get as much literature out there in terms of what these future systems are good at, because we're facing, very high pressure on funding from all kinds of different sources. So next steps in the work, we saw that new digitalized data is already out there from Anna's and Ryan's papers. And extended source modeling has become a thing, basically. And we're working right now on basically quantifying the impact of the assumptions that are baked into the recipes that we're using so that we can see what the error bars are. And one of the problems I'm working on right now is trying to group together different dark matter models into categories so that we can eliminate them all at once. because we don't want to keep having papers that are like, oh, I'm constraining surrounding neutrinos again and again and again, like, you know, and I'm doing the warm dark matter and I'm doing this. So like, hopefully we can just sort of map all of these guys into individual categories. So I was working on this with my undergrad student, Yixin Chen. She was working on basically categorizing if there's a ratio between halo mass function and sub-halo mass functions across the different models. I'm running out of time, so I don't have a lot of time to map here, but basically she identified flexible basic analytical model that was capturing mixed dark matter models, and we were looking at mapping them to sub-halos as well with the help of Xiaolong. And these are my collaborators, and I'm so thankful to have learned so much from them. Thank you so much. And just wanted to put out there a question, I guess, for the questions right now, but to you. I think it would be amazing if we would be able to build as a community basically a publicly available pipeline of actually bringing together the different sources that are constraining the same regime of dark matter. So we have the qualences and a Lyman alpha forest, and the satellite system and the stellar streams are all kind of coming together to the same observable constraint. So right now I feel like the papers are a bit separate, where we're like individually publishing our results and trying to see if we can make joint analysis. But if we could make something where we're all adding to a pool of already existing posteriors, so we can have like a joint posterior, that would be really cool. And similarly for basically having an inference pipeline for all dark matter classes at the same time. Yeah, thank you so much.